evening, everyone. I warmly welcome you all to day 2 of Phase 2 of Robotricks 2021, brought to you by the IEEE Robotics and Automation Society of University of Peradeniya, the student chapter of one of the most recognized and respected global organizations in the robotics and automation industry. I'm Diana Korlege. In Phase 1 of this webinar series, you learned about WebBots, the robot simulation software, and also got a vast knowledge about sensor fusion on the first day of Phase 2. Today, you will be learning about Estimator Design, which deals with the challenge of using onboard sensors and the appropriate map to determine the state of a robot. Sounds interesting to you? Then join us actively to delve into the depths of Estimator Design. With that, let me introduce our guest speaker for today's session. He is currently pursuing a PhD in robotics at the University of Technology in Sydney with a research focus on robot perception, localization, and AI. Being the co-founder of Digital Wellbeing Initiative, he is also passionate about teaching science, communication, and advocating for information literacy. He is also known to dabble in theater, filmmaking, VFX, and game design in his free time. Please welcome Dr. Maleen Jayasuriya. Dear sir, we are so honored to have you today with us. So, on behalf of all the participants, I warmly welcome you to our today's session. Before handing over the session to our speaker, I would like to give a special notice to all of our participants regarding the WebBots evaluation task. The registration deadline has been extended until the 4th of September. We have already received so many applications and you are still not late. So make sure to participate and implement what you have learned in our webinars. Your task is to implement a robot in the WebBot simulation environment. All the participants will be awarded with a valuable e-certificate and the best robot will be awarded with a special prize. In addition, you can have a self-evaluation of what you have learned throughout. So make sure that you don't miss this opportunity. For further details and the registration link, visit our website. Also, regarding the questions you want to get clarified in today's webinar, we will be displaying a link in the chat box through which you can direct them to us so that we will make sure to answer them at the end in the Q&A session. So without further ado, I cordially invite Dr. Maleen Jayasuriya to carry on the session. Over to you, sir.
Thank you, Diana, for the nice introduction. I hope everyone can hear me.
Yes, sir, we can hear you.
Awesome. Okay, so hopefully by the end of today's session, most of you will get an idea about estimator design. Specifically, I'll be focusing on the Kalman filter, right? So, but before we start, just to get an idea of how many of you are familiar with what I'm talking about today, can I get all of you to use Zoom to raise your hands up just for a few questions? First, how many of you are familiar with the Kalman filter? Can I see some hands? Okay, not many people. Okay, great. So hopefully by the end of today, you'll learn something new. All right, so let me share my screen and start today's session. 1 second. I had a power cut just a few minutes ago, so I had a bit of trouble setting everything up beforehand. All right, so okay, I hope everyone can see my screen. Can you see me writing on my screen?
Yes, sir, we can.
Oh, awesome. Okay. So what I'm going to cover today is basically, first I'll give an introduction to this field called probabilistic robotics, right? Probabilistic robotics, right? So this basically treats the design of robots by incorporating our knowledge about probability theory to make sure that we take into account all the randomness and noise that we have to deal with when we're dealing with sensors and things like that, right? So I'll just give a brief introduction to this. Then I will have a quick recap of probability theory, right? So I know everyone from A-level times to even during uni, we cover probability theory, right? But if you're like me, after about a month, we all forget about everything that we learned. So what I'm going to do is I'm doing a quick revision, right? Not an in-depth revision, but a quick recap about probability theory so that we can follow along and understand the rest of the session. Okay. So third, after recapping probability theory, I will give a introduction to the Kalman filter, right? And I will do a simple example using the Kalman filter. It will be a example of a robot moving in 1D environment, right? So that will give you an idea more than me trying to mathematically derive it. I thought I will give you an intuitive understanding of the Kalman filter, how it works. I will also introduce the algorithm, but for the derivation, since we don't have much time, I won't go too much into depth into it. But if any of you are interested, by the end, I will also provide a lot of resources where you can go and read up and learn more if you're interested, right? Once we cover the Kalman filter, I will go into the extended Kalman filter, right? Or the what we call the EKF, right? So I will explain why we have to take into account this idea of an extended Kalman filter. And we'll do another simple example using this, but it will be a more complicated example than what I cover in the Kalman filter, right? And then finally, I will end with sort of practical things to keep in mind. And finally, I will also give you further resources that you can basically look up and learn more if you are interested in this very interesting field. All right, so this is the plan for today. I hope I plan on finishing maybe 1 hour and 30 minutes, 1 hour 45 minutes, and then I'll let you guys have a question and answer session as well. Right, so my main goal today is to give you a very intuitive feeling, right? I will introduce some of the math as well, but I won't go in depth into the math because I feel like you can find those resources very easily, but just the grasping the important concepts is more important, right? Okay, all right, so let's start with this idea of probabilistic robotics. Okay, so if you take a typical robot, and now I think you all have already covered a lot in your phase one, right? So this stuff should be fairly straightforward by now, right? If you take a typical robot, right? Obviously, when we talk about a robot has to autonomously operate in the environment. Autonomously meaning without the input of humans or very little input from the humans, right? So if you take a simple robot like this, let's say a mobile robot with 4 wheels, right? There are a couple of important subsystems that every robot has, right? So if you consider something like what I've drawn here, always an ugly representation of a robot, right? Imagine this is a camera, right? So a robot, initially, one of the main subsystems a robot needs to be able to do is it needs to perceive the environment, right? Just like humans with our eyes and our sensors, a robot needs to understand its environment around it, right? So that's why robots obviously have a lot of sensors like cameras, laser sensors, ultrasound sensors, and things like that, right? So the first subsystem any robot needs is what we call a perception system, right? So it needs a perception system. In other words, just sensors to take information from the environment into the robot, right? Now, once it gets this information into the robot, one important estimation task, right? So I hope you guys are familiar with the concept of state estimation, right? So if any of you are not, what a state is, a state of a robot or state in a system is some sort of quantity or variable that we care about in a system, right? So in a robot, one of the most important states that we care about a lot is what we call the pose of the robot, right? So the second subsystem that really matters when we take a typical robot is what we call the pose estimation system, right? So can someone tell me what is this pose? What's the pose of a robot? Anybody? If you're shy to talk, you can even drop it in the chat. But I want to make this a little interactive so that you guys won't get bored. Whether you like it or not, you're kind of stuck with me for the next 2 hours, right? So help me out and can someone tell me what pose is of a robot? Anybody? Don't be shy.
The location of the robot?
Okay, good. Right. So thanks. Yeah, generally the idea is the location of the robot, but to expand on that idea a little bit, right? How do we mathematically define like the location of a robot? Is that we define it usually in three-dimensional space, right? If we are trying to estimate it in three-dimensional space, then you'll have x, y, z coordinates, right? That will give you the position of the robot. And then you combine this position with the orientation of the robot, right? So when I say orientation, I'm talking about what we call the roll, pitch, and yaw of the robot, right? So roll means the rotation this way, right? Yaw means the rotation this way, and pitch. Let me say that again, right? Roll means this way, right? That is generally around the x-axis of the robot. Pitch means this way, right? That's generally around the y-axis of the robot. And around the z-axis of the robot, this way is what we call the yaw, right? So we'll have the position and orientation, and we'll have three angles, right? Which are called theta, phi, and psi, right? Okay, so the combination of position and orientation is what we call the pose, right? So in this case, if it's a full 3D pose, how many parameters do we need? We need 6 parameters, right? So we say this is a 6 degrees of freedom robot, right? But so for example, if you're dealing with a quadcopter, for example, you will need this 6 degrees of freedom of a robot, right? But if you're dealing with a mobile robot that's going on the ground, if you can assume that the ground is planar, you can get away with just how many? You can get away with just three of these parameters, right? You can say the x, y on the ground and the yaw, right? So that way, if it's a 2D kind of environment, if you can assume that the robot is just traveling on the ground only, you can bring this 6 degrees of freedom to 3 degrees of freedom. Anyway, the point is we need what we call the pose of the robot. Why is this important? Can someone tell me? Any ideas? Anybody? There's 55 people here, so I'm sure at least one of you can answer. Why does a robot need to know its pose? Any guesses?
To know how to move around?
Yeah, right. Very simple answer, right? Because, okay, think about a human, right? If we are walking into a building or walking on the road, we have a pretty good sense of where we are in the environment, right? So a robot has, like, when you create a robot, the robot doesn't have that sense, right? The robot is just there. So we need to build into the robot an ability to know where it is relative to the objects around it, so that it can intelligently navigate in the environment, right? So this pose estimation system is a very important foundational system of the robot, right? So how it generally does this is it takes the information from the perception system, right, to help it estimate its pose, right? So when we talk about state estimation in general, state could be a lot of things, right? State of robot, there are lots of things we care about. For example, the power state of the robot, right? The energy levels. It could be the encoder states, things like that, right? But on a high level, one of the most important states that we try to estimate is the pose, right? Because it's a very fundamental thing, right? Because if you're talking about a system that is intelligent and autonomous, one of the basic things it needs to be able to do is at least know where it is, right? Because then it will avoid bumping into things or crashing into things, or, you know, like think about a self-driving car, for example, right? Like one of the most important things, it needs to know where it is, right? So the pose estimation system is a fundamental system. So once it knows where it is, the next system that matters for a robot is the motion planning and decision-making system. Motion planning and decision, right? So the reason why decision making and motion planning is important is now once it knows where it is, once it's getting the sensor information and it knows where it is, it has to decide what's the safest path that I can go in the environment, right? And once it does that, it can plan multiple paths, and then a decision has to be made which path to follow, right? So that's the third important system in a robot, and it's more of a high level system, right? This is where more intelligence is required and decision-making schemes need to be put into place, right? So all of this has to be done autonomously, like without human input. Once it makes this decision, the next important system that we care about is what we call the control systems, right? Because once it knows where it is, once it has decided where to go, it has to implement the action, right? So that's where the control systems come into play, right? So it will have to control the wheels, or if it's a quadcopter drone, it will have to control the propellers, right? Control the motors running the propellers, right? So that's how it will start to operate, right? So all of this have to work together, right? The perception system helps the pose estimation system figure out where it is. It will give information that is important for motion planning, decision making, and then it will implement it in the control system, right? And then the feedback for the control system will also come from the perception systems, like the sensors, right? So all of this works together. And there's one more system that's sometimes not talked about, and that is the human-robot interface, right? Human-robot interface. This is how we connect, how the human connects with the robot, right? Some robots don't have this, some robots have it. It's an important part of the robot. Some robots, it's not that important, right? But now you have an idea of the important subsystems in a robot, and what we are going to focus on today is this part, right? Because without this part, without the pose estimation, without figuring out where you are, it's very difficult for a robot to do any of these other things. It can't navigate in the environment safely, okay? And this is where state estimation becomes really important. Okay, so as I mentioned before, when you say state estimation, you can be estimating a lot of different parameters. But one of the main parameters that a roboticist or an engineer will want to estimate in a robot is the pose, right? Because it's so important. It's the basic level important parameters that we need to estimate. Okay, so having talked about this and understanding what we're really focusing on today, why did I call this probabilistic? Like, why am I going to talk about probability? Right? I already said that I'll be talking about probability in today's talk. Why probability? Anyone has any guesses? Why do we need estimators and ways to deal with probability? Anybody? Someone say something. Now there's 62 of you. Right? I'm sure some of you have some idea. Don't be shy. Right? No one is going to laugh at you. Any ideas? Why is probability important? Someone said because there are different paths a robot can take. Okay. Any other answers? Making decisions.
To take right actions.
To take correct actions. Why is probability important in that? Like, you can make certain decisions already, right? You can say, like, I should always go forward or something. Why is probability such an important part of this? Okay, so the reason probability is really important is when we talk about the main ways information is coming into the robot and the way the information is given out from the robot, that is basically the perception system and the control systems, both of those are never perfect, right? When you talk about sensors, there are so much noise in sensors, right? We already know this, right? When you're using some sort of sensing equipment to measure something, even a ruler, right? It's not 100% accurate, right? There is always a noise associated or errors associated with it, right? So the reason we have to think about probability is because there is one sensor noise, right? Okay, so when you're getting information from a sensor, if the sensor is saying, okay, I'm seeing something there or something like that, the accuracy of that is never 100%. Okay. Secondly, the control signals are also never 100% noise-free either, right? The control execution, right? So for example, if I tell a robot, I want you to move 5 meters forward, will it be able to exactly move 5 meters forward? No, right? There will always be some sort of noise involved, right? Like there'll be noise in the encoder readings. There'll be noises in the execution of the motor. There will also be slip on the ground, right? So there's always going to be all these noisy problems, right? So nothing is 100% perfect. Because of this, right, now most of you during A levels and maybe half of your undergrad as well have been dealing with what we call deterministic systems, right? Deterministic systems are basically where you have an input, you have an output, and it's perfectly mapped, right? So for a very simple example, let's say you take the equation F equals ma, right? If I plug in M and I plug in A, I will get the force, right? But in the real world, when you're measuring the mass and you're measuring the acceleration, there'll be noise with it, right? It won't be a perfect measurement, right? So the thing is, when you're trying to, for example, find the pose of a robot, if you don't take this into account, the thing is the answers that you get won't be very accurate, right? So what we try to do is we try to take into account the fact that our sensor information and our control signals are noisy, right? And we try to model that using our knowledge about probability, right? And this is something, as you get more and more advanced in engineering, most of you, I think in third, fourth year, will start to learn more of these probabilistic techniques. Even in telecommunication, even if you send an SMS from your phone, you can't 100% guarantee that the message or the information in the message will be received on the other end, right? So the best thing to do is, instead of using deterministic systems and pretending like everything is perfect, what we do is we try to model the probability into the system, right? And systems where the probability is kind of incorporated into it are called stochastic systems, right? Stochastic systems, right? So the more and more as engineers we go out into the real world, we will have to start learning more and more about stochastic systems rather than deterministic systems, right? That's how we have to, in most cases, have to deal with real world situations, right? Whether it's telecommunication, whether it's robotics, whatever, right? So what I'm going to teach you today, like the Kalman filter, is one way of trying to, instead of trying to find a perfect answer, what it tries to do is it tries to give you the best answer and also give you an understanding of the uncertainty, right? So it will never tell you, I know exactly the answer. It will tell you this is the most probable answer to this amount of certainty, right? And that is better than pretending to know the answer, right? I hope everyone can understand that. Like, for example, let's say there's a robot, right? And it's close to a cliff, right? So let's say there's a big drop like this. It will fall if it's close by, right? Now, in reality, the pose of the robot, we never know for sure where it is, right? So, for example, if you have something like the Kalman filter, it will tell you the robot is somewhere here, right? But it will not only tell you where it is, where it's most probably going to be, it will tell you that it will give a certain uncertainty. It will say the robot is most probably here, but at an uncertainty, it could be in this area, right? So kind of like when we say, we give a reading and we say plus minus whatever, right? So that way, the robot can make more intelligent decisions, right? For example, if the Kalman filter says, okay, the force estimate is here, but my uncertainty is very large, then the robot knows, okay, I have to be careful now. I have to take it slow. And because next to me is this cliff and I could fall, so I have to take it slow. But if the Kalman filter says that I am very, very certain of my location, that this is my location and I'm very certain of it, then the robot can decide to be more confident, right? So that's the approach that we have to take when we are trying to deal with probability, right? Rather than saying exactly the answer, we kind of say, we guess, or not only guess, we say this is how certain, right? And that's how you deal with a stochastic system. And that's why we need probability theory and statistics. Okay. And that's why we need something like an estimator, like a Kalman filter, rather than just having a set of equations, right? So most of you are already just familiar with sets of equations, right? You would have a system equation, you would plug in the values and you will get an answer, right? But that doesn't work in the real world in most cases in engineering. right? The best thing we can do is we have the system, but we also model the what we call the uncertainty, right? Like how sure are we of our answer, right? And the Kalman filter is a very powerful tool to help us do that. Okay, so I hope this gives you a good feel for why we want to, good introduction for why we want to use probability and why we use something like the Kalman filter. Okay, so before we move any forward, are there any questions, or is this so far clear for everyone? If it's clear, just give me a thumbs up in Zoom. I think you can use the, okay. Because it's very hard to do these lectures without seeing anybody. So I would appreciate some sort of quick feedback so I can move forward. Okay, so I see 2 thumbs ups. So that means everyone else has no idea what I'm talking about. Okay, I'm seeing more thumbs ups. Okay. All right, so now I hope everyone has a basic understanding why we have to think about probability when we are looking into these things, right? Because our sensor information is not perfect, our control execution is not perfect either. Okay, so now we'll have a quick recap of probability, right? And this might, for some of you, this might be things that you already know. But as I said before, like having been in university, after about a month, you forget everything, right? So I'm just going to quickly run through everything so that it's fresh in everyone's mind and the rest will become easier. Okay, so now we move to the second part, which is probability theory recap. Okay, so we are first going to start off with this concept of a random variable. Okay, so does anyone know what a random variable is? Anybody? Okay, so when all of you guys end up, I'm guessing y'all are all university students. So once all of you all end up in the industry or once you all leave university, you have to become forward, right? Otherwise, it's going to be very difficult for you all to progress in anything, right? So I think in most of our universities, we are all scared to talk, or including me, right? I used to be that way as well, but it's really important that you step forward and share your ideas. Otherwise, other people will put you down and they'll move forward. Okay, so if any of you, don't be shy, just step up and tell me, does anyone know what a random variable is or has any idea? Okay, I'm getting some in the chat. The variable that used to model a probability. Okay, good enough, right? So a random variable is basically, it's a variable, right? Something like X, whose value depends on some sort of random event, right? So the value depends, or the outcome, or value depends on the outcome of a random event. Okay, so when I mean random event, it's some sort of thing that is uncertain, right? So a classic example that we are all familiar with is flipping a coin, right? So that is a random event, right? And the value of the what we call a random variable will depend on the outcome of that event, right? So for example, if you think about flipping a coin, right, we will have heads or tails, right? And this will be our what we call our sample space, right? So a random variable is what a random variable also does is it maps these events into real numbers, right? So for example, I can say getting heads is +1 and tails is -1, right? And this gets mapped to these values, right? And the outcome of your random event, the value of this X, whether it's +1 or -1, depends, is uncertain. We don't know, right? It can be +1, it can be -1. While as normally when we say X, there's an exact value, right? Like when we were in A levels or whatever, when we solved X, we would get a value, right? But here it could be either 1 or -1, right? And that's why it's called a random variable, right? So its outcome depends on the uncertain random event, right? So you'll have +1, -1. And someone said it helps us model probability. Yes, right? So we also know now that, so for example, X here is outcome of a coin flip, right? So the way we talk about probability here then is we say, what is the probability of this outcome equaling +1, right? That, or in other words, heads, right? And obviously we all know if it's an unbiased coin, it will be 0.5. Okay, and then we would say, what's the probability of X being -1, which is heads, tails, and we would say 0.5, right? For, if it's an unbiased coin. Okay, so what I want to show you guys is this is how we normally write probabilities, right? We say probability of X equaling a certain value. Okay, so in this case, this flipping a coin example, you can also draw in a graph the distribution of this Px of simple x, right? So simple x is usually the value here, right? So either x is the random variable name, simple x is the particular event, right? +1 or -1. Okay, so if you just simply draw this, we know that we will get for -1 here 0.5 and +1 here 0.5, right? So this is called a probability mass distribution. Why is it called a probability mass distribution? Because this random variable is a discrete random variable, right? So all of you know the difference between discrete and continuous. In this case, the heads or tails is a discrete random variable. Okay, and if you are dealing with discrete random variable, this is called a probability mass distribution. This is called a probability mass function or PMF. Okay, so most of you probably already know this, but I'm just quickly covering it, right? And another important thing that we need to know is the sum of these probabilities equals 1, right? Or the sum of the probabilities. Okay, so this was a discrete example. Let's quickly talk about a continuous random variable example, right? So if I take a continuous random variable, what are continuous random variables? Basically, unlike discrete, you can have multiple. You can have continuous values, right? So simple example for this is, let's say our variable is x, right? And a simple example is height of students at Pera, right? So if we take everyone's heights and measure them at Peradeniya University, we will get a distribution of all possible heights, right? And since height can be any value, right, what we get is a continuous random variable. Okay, so just like we had the probability mass distribution, you can draw what we call a probability density distribution, right? So probability density distribution for something like for height of students will look something like this, right? So this will be given as P of x, right? And here we will have x. Okay, so unlike the discrete situation, we have what we call a continuous situation, right? And this is a probability distribution function. Probability distribution, sorry, probability density function. Right? So if it's continuous, it's called a probability density function. All right, so this shape here is what we call a Gaussian distribution, and I'll talk a little bit more about that because it's important in Kalman filters. But before we get into that, some important things. For example, we can never. Okay, so let's say this is the height of students, right, and Pera, and let's say the average height is 1.75 meters, right? Sorry, that's a bit tall, right? Let's say 1.5 meters is the average. Okay, and then we have 1.75 or whatever, right? So the reason we get a distribution like this, what we call a Gaussian distribution, is because obviously there'll be only a few people who are really tall and only a few people who are really short, right? So if I come to Peradeniya and I measure everyone's heights, right, we'll most probably get a Gaussian distribution like this, right? We'll have only a few people who are really tall, only a few people who are really short, and most people will have an average height, and that's why we call it the mean or the average, right? Okay, so now in the discrete case, I can ask, okay, what's the probability I get +1, and I can get the distribution like this, right? And I can say, what's the probability? 0.5. Can I do the same here? Can I say, what's the probability that I will get 1.7? Okay, so most of you will think, okay, it's easy, right? You just have to find 1.7 here and then find the probability. Is that correct? How many of you say it's correct? Can you raise your hands up? Or give a thumbs up if everyone thinks that's correct. Okay, how many of you think it's wrong? Okay, we have 1, 2, 3. We have someone said wrong. Okay, so one of the people who said wrong, can you all explain why it's wrong? Why can't we just say p of x equals 1.7 and just find this value? Okay, so the reason, so people who said wrong are right? You can't do this because if you take this particular value here, right, we never can find this value, right? Exactly 1.7. Like, yeah, like for example, if I'm measuring people's heights, we can never find someone who's exactly 1.7, right? You can have 1.70001 or 1.655 or whatever, right? So the probability of finding someone who is exactly 1.7 is 0, right? Because you can't physically actually get a certain specific value, right? So all you can do is you can get ranges, right? So for example, when you're dealing with a continuous distribution, all you can ask is what's the probability that x is between, say, 1.69 and 1.71, right? So in that case, what you would normally do is you would find the area under this curve, right? So which is why if you take a probability distribution, you have to integrate the area to actually find the probabilities, right? So that's a basic important concept that everyone needs to know. You can't exactly find values because you can never find something exactly, right? Because if you find the probability of finding someone exactly at that value is 0. Okay. All right. So you would have to integrate and get the area under the graph to find it. All right, so before we move on, any questions regarding this? So this is just basic recap of probability here. Okay, if there are any questions, just put it on the chat or stop me anytime, right? Okay, so now that we learned about the basic concepts of probability distribution functions and probability density functions and distributions, I want to talk about a special type of probability density function, which I'm going to call PDF. And that is the Gaussian distribution. So as you saw with this height example, it's very common to find this Gaussian distribution in nature everywhere, right? Like if I came to Peradeniya and I not right now because of COVID, but in a usual time, if I measured everyone's heights, it will most probably be in this distribution, right? So this shape is common in nature everywhere, right? So so what we do is we specifically study this Gaussian distribution, this specific shape, because it can help us solve a lot of problems because it's naturally occurring everywhere, right? There will always be outliers, right? Really tall people, only a few of them, and really short people, only a few of them, and most people will be in the middle, right? And that's the nature of most quantities in nature, right? There will be an average and there will be outliers on either extremes, right? Which is why we find these Gaussian distributions in nature a lot, right? Another name for Gaussian distributions is normal distribution, right? So just to talk a little bit about the properties of Gaussian distribution, because this is going to be very, very important for the Kalman, right? Because the biggest assumption in the Kalman filter is that everything is Gaussian, right? So I want all of you to really follow this section because it will really help us understand the Kalman filter next. All right, so if you take a typical Gaussian distribution, we already saw the shape of it, sorry, right? And it looks like this, okay? So if I take a Gaussian distribution, right? this, right? Everyone has seen Gaussian distributions, right? And the middle value is what we call the mean, right? And the symbol for the mean is mu. So the mean is kind of the average value, right? And then another important quantity in this Gaussian distribution is how much it's spread, right? So the spread of it is given by a quantity called the variance, right? Sigma square, right? So the variance, I'm sure most of you have already studied it, measures the square distance, right, from the mean, like how far away it is from the mean, how much it's spread. So a high variance means the graph will look like this. A low variance means the graph will look like this, right? More centered around the mean. Okay. And this will be a high variance. So if sigma squared is high, and then sigma squared is low. Good. All right. So these are two important quantities, because if you write the equation of this graph, right? This is just a graph, right? So we can actually write its equation. So if you write the equation of this graph, this is what it looks like, right? Let me quickly double check before I write it. Gaussian equation. So if I remember correctly, it's, I'll just use px here. It's 1 over root 2 pi sigma squared e to the power. 1 second to double check. I don't want to give any of the wrong equations. Right? E to the power minus half x minus mu squared divided by sigma squared, right? So you can see here, this is a kind of an exponential kind of graph, right? And this equation tells you about this graph. And you can see that there are two important, these two quantities, this equation has been written in terms of those two quantities, right? So you can see here there's sigma and mu, right? What this means is, all I need to describe a normal distribution or a Gaussian distribution is this sigma and mu, right? So usually when we write this graph, we just write it like this. We just give the mu and sigma values, right? Because if someone gives you the mu and sigma values, you can easily draw this graph, right? Because all you have to do is plug these values here and draw it, right? Or you can draw the mu here and figure out the spread, right? So this is an important quality, because that means you don't have to write this whole equation. This entire graph is captured by these two quantities, right? And this concept is called parameterization, right? So the reason it's called parameterization is because I have used two parameters to describe this whole function. I have parameterized this function using these two quantities, the mean and variance, right? So if anyone tells you the mean and variance of a Gaussian distribution, you know the whole graph, right? I hope that makes sense. Okay, so the entire graph can be described using these two. So normally you can just write your normal distribution like this. Right? So for example, mu could be, in our previous example, mu was 150, right? And then there'll be some sort of sigma here, like sigma squared, right? Maybe 5 or something. Okay, depending on the spread. Okay, so that's, I hope, clear. Another thing that we need to understand here is about information, right? So these graphs capture information. Okay, so can someone tell me, if I have a graph like this, draw two Gaussian distributions, and then I have one like this. Right? In this case, sigma is what? Sigma square, the variance is very high. In this case, the variance is very low. Can someone tell me, okay, actually, since no one wants to answer, can you all at least give me thumbs ups, right? How many of you all think that the yellow curve, which has a high variance, has more information than the green curve? more information about something. We have 1, 2. Okay. How many of y'all think the green curve has more information than the yellow curve? Gives us more information. We have 2 again. Everyone else has no. Okay, we have 3. How many of y'all have no idea? Okay, I hope everyone else is not like dead or something. I can't see anyone responding. Okay, I hope, yeah, I hope you guys are listening and still with me, right? Okay, so obviously the information here is less than here, right? Because when the variance is small, what that's saying is we are more and more certain about something, right? So whereas in this case, we are very uncertain about this, right? So for example, let's say if you are taking a particular value out of this, there is more uncertainty in this yellow graph than in the green graph, right? Because everything is more closer to a particular value, right? So it's more closer to the mean. So we are more certain of the quantity that we're looking at more than the yellow graph, right? So to capture this, there is a definition of information that is really important for us, right? This is called Fisher information. And what it basically says is information is inversely proportional to the variance, right? That means the higher the variance, the less the information that we have. The smaller the variance, the more information we have on a particular thing, right? So this might not make that much sense yet, but once we go into the Kalman filter, this I just remember this fact, right? That your information is inversely proportional to sigma. Okay, and things will be a bit more clear. The other thing I want all of you all to remember in this recap is, let's say you had the following random variables, right? Let's say you had 2 Gaussian variables and you want to combine them or understand what happens when you add the random variables together or multiply by a normal or something like that, by a constant or something like that, right? So for example, let's say I had a random variable like this, right, which is normally distributed, and let's say its mean is mu, right, and its variance is sigma squared, right, and let's say I multiply this random variable by a constant a. If I multiply this by a constant a, what happens to the distribution is simply you just multiply the mean and multiply by the square of the variance. Okay? So if you had this distribution and there's just a multiplication by a constant, right, you will get this distribution. Okay, so that's one important property of the Gaussian distribution. So we're talking about the properties. So this will be property 1. Again, this is all going to be important when we're talking about the Kalman filter and trying to understand it. Property 2. Also, you can kind of understand this as well. Imagine you take one of these graphs and you multiply it by a constant. Right? Think about what's going to happen to the mean and what's going to happen to the spread or the variance. Right? Property 2 is, let's say you had you add something to something, right? So let's say you had x plus, say you're adding a certain value m to it, right? What will happen then is you will have the same normal distribution n, and what's going to simply happen is your mean is going to shift by this value, but your variance is not going to change because you haven't multiplied anything by, you only shifted the mean, right? So if you add something to the random variable, only the mean is going to shift. Again, if you think of that height example, hopefully it will be clear, right? Because in the height distribution, if I just decide to add 0.5 to everyone's readings, the spread is not going to change, but the mean is going to shift, right? So that's something, that's the second property you need to understand. Then property 3 that everyone needs to know is, let's say you had 2 Gaussian distributions, right? So this random variable is distributed in a Gaussian distribution, right? So you had this, and then you had, I'll call this mu1, sigma 1, And then I had y, which is normally distributed as well, with mean mu2 and sigma 2 square. Now let's say I added these two up. Can someone tell me what's going to happen? What's going to happen to the mean and the variance? Any ideas? Are you guys still here? Can you guys hear me? Am I just talking to a screen? Does anyone know the answer to this? What would happen if I sum the two things? Mean would be the addition, good, right? So the mean would be mu1 plus mu2. And what about the variance? Variance will also be the addition, right? So you have sigma 1 squared plus sigma 2 squared. Yes, okay. So I want you guys to remember these properties. Right? So this is basically the revision of probability that I want all of you all to keep in your mind. Okay. So going back to what we are going to talk about today, I've so far given you an introduction. I've given you a recap of probability. Now we are going to jump into the Kalman filter, the most important part here. Right. So for all of this, all of what we talked about before is important. Right. Your knowledge about probability and your knowledge about Gaussian normal distributions becomes very important. Okay, so before we move on to the Kalman filter, if there are any questions, you can ask me now. Especially about this probability part, if any of it was not clear, please ask me now, because otherwise it's going to be difficult to understand the Kalman.
So is there reason to use specifically Gaussian distribution for Kalman filters? Or
so there's no particular, in the sense it makes things easier. It's an assumption, right? So in the Kalman filter, we assume everything is Gaussian, and for the most part, it's a good assumption to make because it makes things easier. But in reality, there are some examples where you don't have Gaussian distributions, and in those kind of cases, you have to use different estimators, right? So the Kalman filter is like the first level estimator that you would use, and in most cases, it works very well. But if it doesn't work, then you have to, then your assumption that something is Gaussian might be wrong, and then you might have to use a more complicated estimator, right? So, for example, today I'm going to talk about Kalman filter, then I'm going to talk about the EKF, which is a bit better than the Kalman filter, and then we don't have time today, but one level above that is something called the particle filter, right? And there are more different types of estimators to help you understand. To do the estimation, but that's a really good question. There's no particular reason other than the fact that you find Gaussian distributions in nature a lot, and it's a reasonable assumption to make, right? But it is an assumption. Okay. So what are the assumptions? There are actually two assumptions we make when we talk about the Kalman filter. One is that everything is a normal distribution, right? Normal distribution or Gaussian distribution. The other assumption we make in the Kalman filter is that the systems are linear. Right? So by linear, we mean that there are no cosine, there is no squared values, nothing like that, right? So all the systems that we're dealing with are linear. So these are the two assumptions that a Kalman filter has, right? And the assumptions are there, as you know, to make things easier, but you know, sometimes those assumptions break down. So you will need to be aware of what the assumptions are, and if something is going wrong, you'll have to try something more advanced, right? Or figure out ways to get around that assumption, which is what the extended Kalman filter does to a certain extent. It deals with this assumption of linearity, but even in that, it assumes that you have a normal or Gaussian distribution. Okay, so good question. Any other questions? Someone said as last part, once the two informations were added, the variance was increased. Yeah. So Yeah, we will actually come to that when we're talking about the Kalman filter. You'll actually see how variances are added, and it will be a bit more clearer, right? Okay. All right, so let's talk about the Kalman filter now, right? Before moving into the Kalman filter, let's talk about a little bit about localization and what we're trying to do in this case, right? So we are trying to estimate the force of the robot. Right? And what we're trying to do is we're trying to basically figure out where the robot is based on the things that we have in the robot, right? So I'm going to first, to give you all an intuitive understanding, take a simple 1D example. Okay. So let me just have a sip of water. Okay. So let's take a simple example of a 1D robot. Okay, and I'm going to go through the Kalman filter algorithm, right, through this 1D robot and show you how everything is done, right? Actually, first I'll give you guys the algorithm, right? So it might not make much sense, right? But imagine we have a robot in this location and we move forward, right? When the robot moves forward, we give that robot some sort of control signal, right? We tell the robot move forward, right? So what we call that is the control signal. Okay, so imagine these are two time instances, right? So this is at time k and time k plus 1. Okay, and as we go here, there'll be k plus 2 and k plus 3 and so on, right? So we are looking at this in these discrete time steps. Okay, and at k, what we consider the pose of the robot, we'll call that xk. And the pose of the robot here is xk plus 1. Right? So what we have is a control command called ut. I'm going to, sorry, not t, I'll call this uk. So this control command tells the robot to move forward, and it takes the robot from xk location to xk plus 1, right? And then at the same time, the robot has a camera, right? Or some sort of sensor, right? So there will also be sensor readings coming into the robot, right? So you have zk and zk plus 1 and so on, right? So I'm just introducing you all to the terms that we are going to use, right? So xk is what we use for the pose, right? Uk is what we use for the control, and zk is what we use for the sensor information, right? We also call these observations. So if you take a typical robot, right, any robot, right, whether it's a 2D, 3D, or 1D robot, these are the information that we have coming into the robot, right? All the variables that we have to deal with. What are we interested in is basically these poses, right? That is based on the control signal and based on the sensor information that we are coming in. How do we find these poses? And that's the problem of pose estimation, right? And as I mentioned, there are two pieces of information that we can measure. We can measure the control or the control signal we are giving, because we are giving the control signal. We have this piece of information. Also, the sensors observations are coming in, so we have this piece of information as well. So using this information, the question is, how can we figure out the pose of the robot? Okay? Or not just figure out, estimate, right? So I'm using the word estimate here because, as I mentioned, you will never be able to 100% answer this question. You'll only be able to estimate, right? Okay, so I hope everyone is clear about the different systems here and the terminology. All right, so now I'm just going to give you guys the Kalman filter algorithm, right? And explain it a little bit and then go through a simple 1D example. Okay. All right. So you have the Kalman filter. algorithm, right? So I'm actually going to write it like you would write a function on a computer, right? So what are the things that we're giving as input, right? So the way this algorithm works is it's a recursive algorithm. So can anyone explain what recursive is? Does anyone know what a recursive algorithm is?
Something that happens over and over again.
Kind of, right? So in a recursive algorithm, what you do is you take the previous step's answer to find the current step, and then you use that current step as the previous step in the next step, right? And like you said, something that happens over and over again, right? So you have to start with something that you know, and then feed it into the algorithm, and the output of that algorithm goes back into the same algorithm, right? So that's kind of how this Kalman filter algorithm works as well. It's built in a recursive way, so it's very easy to write a code for it as well, right? You just have to write a function in the way I'm talking, in the way I'm going to present it, and then it can go recursive, right? So before we actually get into this algorithm, a few more things that we need to understand, right? So there is something called a motion model, which basically takes your, it's a function that will take your pose information and your control information and tell you what's going to happen next based on this control information, right? So very simply, let me just write it in the most general form and then I'll explain it, right? So what a motion model does, it says what xk plus 1 is, right? How basically it's a function that takes in xk and the control command and tells you what xk plus 1 is going to be, right? So for example, very simply, let's say you're at a location, in your previous step at xk, you're in location, let's say you're in a 1D scenario, right? And let's say the robot is here, right, at 2, and here is 0, right? So xk is going to be 2, right? And then uk is the control command, right? So typically the control command will be something that you can measure using your encoders or IMU or something like something that measures the motion, right? That gives you the feedback for the control, right? So for example, it will uk is typically like the velocity of the robot, right? So let's say the velocity of the robot is 5 meters per second. So you would input this 5 meters per second and you would get what xk plus 1 is going to be, right? So basically what the motion model does is it gives you the relationship between the current state and the next state based on the motion command, right? So very simple motion model here in this 1D case, right? Let's say the time instance here, the time difference between xk plus 1 and k and xk is going to be 2 seconds, right? So what's xk plus 1 going to be is simply going to be 2 plus the velocity into time, right? So it's going to be 2 plus 5 meters per second into 2 seconds, right? So in these 2 seconds, xk plus 1 is now basically 12, right? So this is going to be the motion model, right? So let me actually just write the motion model again. Xk plus 1 equals xk plus your uk, which is the velocity, times delta t. Okay, so this is an example of a motion model, right? So what does the motion model do? It takes the current state, right, and the motion command and tells you where you're going to be next, right? And we consider this to be what we call a prediction. Okay? Because again, although I wrote it like this, none of this is certain, right? Because this control command, this velocity, although I said it's 5 meters per second, we don't know exactly whether it was 5 meters per second, right? And even if we measured it as 5 meters per second, if the robot slipped on the ground, right, even if the actual measurement is correct, and it's 5 meters per second. If the robot slipped on the ground, it will stop at somewhere like 10, right? So this motion model we consider as some sort of prediction of where it will be based on the information of this control. Remember, as I mentioned, there are two pieces of information. We have the control and we have the observation, right? So typically, this motion model, when you use just the control information, typically what happens is we become more and more uncertain, right? Because if you think about it, if we didn't have any sensor information, right, and all we're doing is looking at this velocity information and predicting the next step, will that be accurate? No, right? It's kind of like, imagine all of you decided to close your eyes, right? There's no sensor information, and all you have to navigate is to count your number of steps, right? So imagine you're standing in one place and you close your eyes and you just count your steps, right? Obviously, there are going to be small errors there, right? And what happens is, since this is a recursive algorithm, right? Since xk plus 1 becomes the next xk, right? That's what it means to be recursive, right? So for example, now you go from 2 to 12, in the next step, 12 is going to be a xk, and somewhere in front is going to be a xk plus 1, right? So if you make a mistake here, that mistake gets added onto that, and that mistake gets added onto that, and so on, right? So what happens then is your answer, your final answer, because none of these UK values, or basically this velocity value, which I'm calling UK to be general, is never going to be accurate, right? Because you're measuring it using something like an encoder, right? I'm sure all of you know what encoder is, or something like an IMU, right? And you're measuring it, the measurement itself is uncertain. Plus, as I mentioned before, when the robot is moving, it can slip and some things can go wrong, right? So because of that, it's kind of like you're closing your eyes, no observations, you're just counting your steps and navigating. And that's a very dangerous way to operate. And as time goes by, your answer will get worse and worse and worse, and we call that drift, right? So you will drift, okay? So if you only look at this control signal, can we get an accurate answer? No, right? Sometimes it's good, but for the most part, just looking at these control signals is a bad way to navigate. That is why most robots have this sensor information as well, right? Some sort of camera or laser or ultrasound sensor that will basically get information from the environment, and what it will do is it will correct this error, right? This prediction. So remember, the motion model, there's a prediction. It predicts where everything is going to be, and then the observation helps us make that prediction a little bit better, right? So for the observation of the sensor, just like we have the motion model, we have something called an observation model. And don't worry, I will do concrete examples and then this will be a bit more clear, right? So we have something called an observation model. So what an observation model does is, right, it figures out what the observation is, right? So is it k plus 1 given? So I'm going to use h as the function. Given your current location, right? Yeah, basically given your current location, it will tell you what your observation is going to be like, right? And that's what the observation model does, right? And the inverse of this observation model basically captures what we want, right? Given my observation, where am I most likely to be, right? So you can actually write this in a probabilistic fashion as well, right? And I hope this will be a bit clear for most of you. Motion model, if you write it in a probabilistic way, what we are saying essentially is, what is the probability I am in a particular new location given my previous location and my control commands, UK, right? While as the observation model gives you the probability of what is my current observation given my previous, given my current location. Okay, so that's basically, you need to understand these two models, right? What I mean by model, I hope this example makes clear, right? It's just an equation that will map, it's just a function that will map this information to this information, right? And the same with the observation model. Like, for example, if you're looking through a camera and getting a piece of information from the camera, there has to be some way to relate the observation to your current location, right? It will be an equation, right, between the camera's information coming in and your current location, right? So I'll do an example and this will be a bit more clear. But I hope it's clear, this motion model and this observation model. Okay, so now when we are dealing with these models, all of this is going to be in probability, right? So although I wrote these functions, the actual quantities that we're going to estimate are not going to be exact answers, right? It won't be like what I did here, where it's exactly 12 or 10 or anything like that. Rather, what we're going to find using this is the distribution itself, right? So that when we get the whole distribution, we can query it and say, okay, what's the probability I'm in this particular location and so on, right? So that's the difference between a deterministic system and remember what I called a stochastic system, where we are dealing here with probabilities now. Okay, so these equations exist, but the actual quantities that we are going to estimate are probability quantities. And since the Kalman filter assumes that everything is Gaussian, right? That was assumption number one, Gaussian or normal. What are the quantities that we have to estimate in a Gaussian distribution? Is simply its mean and its covariance, right? So as long as we can estimate its mean and covariance, we are pretty much estimating the entire probability of the system, right? So the mean will give us the best, like the most average estimate that we can assume, right? So the final answer should be the mean that we should take into account. And the variance here will tell you how sure of your answer you are, right? Again, I will do a simple example now, and this will be a bit clearer. So into our algorithm, what we have to input, right, is actually the mean, right? The mean of the system, right? So let me write this as we are writing the algorithm. So when I say xk here, I mean the mean location, right? So let me say, I'll just call this thinking of this notation for this. I'll call this mu. Or give me 1 second to double check the notation that's mostly used, and then I yeah, so we'll just use xk, right? So when I mean xk here, remember I'm talking about the mean of the distribution, right? Because that's the best answer we can get, right? Now when what this filter is going to estimate is both the mean and the variance, right? These two quantities of our distribution. So when I'm talking about the pose of the robot, I'm never going to give an exact value. All I'm going to do is figure out this distribution. And then if I want an exact value, I'm just going to assume that the mean is the best answer, right? So when I say xk, this is what I'm talking about, right? But just saying xk is not enough. I will also have to give the sigma value, right? The variance of the system. Okay. All right. So into the algorithm, what's going to go in is going to be simply xk. That is the previous step. Remember, this is recursive, right? Xk, and then we are also going to include sigma k, right? That is the variance of the system. Then what else is going to get inputted is basically our control system, control signal uk, right? Along with it, the other thing we are going to input into this is our observation, right? So zk. Actually, the observation at this step, which is zk plus 1. Okay, so imagine the robot has taken a step forward, right? We have measured this control command uk, and then it's taken in an observation, which is zk plus 1. So the input to this function are going to be these, right? It's going to be the current location xk, the control signal uk, right? And the observation is zk plus 1. Okay, and that's what's going to go into the Kalman filter. Okay, so now what happens inside the Kalman filter are 2 steps, right? So the first step is called the prediction step. Okay, so in the prediction step, we simply use the motion model that I was talking about, right? So the motion model is what maps the current state to the next state, right? So xk plus 1, you put in some sort of function, right? That maps xk and uk. Okay, and the output of this function is going to be a prediction, right? It's not going to be our final answer. It's going to be the prediction. So we are going to put a bar on top of it to show that it's a prediction. Okay, so remember, this is a probabilistic system, right? So along with this function, we are also going to model the noise of this function as well, right? So I'm just going to, I'll actually write this out. I'll actually write this function out in a more, what do you call it, expanded fashion, right? So that it becomes more clear. So I'll just write it like this. Some sort of matrix F, right, multiplied by xk plus g multiplied by uk, right? And so what you're putting into this, you will get a prediction forward saying, okay, this is the predicted next location, mean location, right? Because this xk, remember, is the mean of the function. So there are 2 things we have to estimate here. Not just the mean, we need to also estimate the variance, right? So the next step in this prediction step is we need to calculate the predicted variance as well, right? So in this prediction step, we also need to figure out the predicted variance, pk plus 1. So the predicted variance in this case, in this equation, and I'll explain the equation using an example, is simply going to be our function f multiplied by the previous sigma k, which you inputted here, right, into f transpose. I hope everyone knows basic linear algebra, right? So f is, in most cases, going to be a matrix, right? Now, in this simple 1D example, it's not a matrix because it's just one quantity. But remember, the poles is x, y, z, roll, pitch, yaw. Right? So there are actually 6 quantities, right? So this function will be a multivariable function, right? There will be multiple values. It will be a matrix, not a simple equation. But I'll do a 1D example, so it will be a bit more clear, right? So if you're dealing with multivariable systems, right, your Gaussian distribution will also be multivariable. It will look something like this, right? Now we've been drawing this 1D Gaussian distributions, but in reality, when you're dealing with your robot, since you're dealing with multiple variables, you have these multiple Gaussian distributions, right? A multivariate Gaussian distribution. So in this algorithm, you get f into sigma ft, right? Which is the transpose of the matrix. Again, I'm just putting down the equation now first, and then I will explain with an example, okay? And then it will be a bit clearer. So I'll just write this out first. Plus what is called Q. Q is the noise in the control signal, right? So some sort of Gaussian noise in the control signal. So for example, we would have a general idea using experiments how much noisy my control signal is, right? So Q tells you how noisy your control signal is. So this 2 steps makes the prediction, right? And what it's essentially doing is it's predicting the mean and the variance of our Gaussian distribution. Okay? To be a bit more rigorous with the notation, instead of sigma, since we are dealing with a multivariate Gaussian distribution, I'm going to use big sigma, right? Instead of little sigma, right? So if you're dealing with a 1D example, this becomes simpler, and I'll use the 1D example first. And then in the second stage, I will use a full multivariate example. Okay. So this is the prediction step. And then what happens after the prediction step is now we are predicting how it's going to move forward. Now we need to take into account the observation, right? So after the prediction step, we have what we call the update step. So in the update step, what we do is we take this predicted information and we combine it with the observation that we got, right? So how we combine it with the observation that we got is we say xk plus 1 hat means estimate, right? This is going to be a final answer. Okay? Actually, I'll put a hat on top of this as well. So since it's a estimate, okay, it will always be x hat like this, okay? Because we never know what the final exact answer is. To indicate that it's an estimate, we use this small hat icon, right? So this is going to be a prediction. We use the bar to say it's a prediction. So what we're going to do is use that prediction and we are going to combine it with the observation, right? So, and then get our final answer. Again, this is our mean of our answer. And then we'll also have to estimate the final variance as well, right? So in the case of a multivariate Gaussian, that means a Gaussian with more than one dimensions, this variance is called covariance, right? It's a matrix that captures all the variance in each of the directions, right? Don't worry too much about it. But just remember, unlike the simple sigma, right? This capital sigma is actually a matrix. It has all the variances of each of the quantities that we are looking at. So this is actually called covariance, right? But in a 1D case, this becomes sigma squared. Okay? Same concept. The covariance captures how much it's spread. Okay, so how do we actually get these two final answers? So to get these two final answers, we take our prediction, which is xk plus 1, right? And then we multiply it by something called the Kalman gain, and I'll show you how to calculate it, into the difference between the observation minus the observation model using the predicted observation. Okay, so remember the observation model here that I wrote, which is this. That means it maps your current state to the observation. It predicts the observation that you're going to see, right? So by finding the difference between the actual observation and the predicted observation, and if you multiply it by this thing called the Kalman gain, you can combine these two information together. Okay, so again, I'm just putting this algorithm down and then I'll explain in more detail. To calculate sigma square, what we do is you take the previous predicted sigma k plus 1 that you calculated in the prediction step, and again you subtract by the by k into what we call the innovation covariance into kt. Again, what the innovation covariance and this k value is basically calculated like this. So k is called the Kalman gain, and the k is calculated as actually before k we have to calculate this s value, right? So this S value is calculated using this equation. It's simply your observation model times the predicted covariance into its transpose plus R. So Q was the noise in the control signal. R is the noise in the observation, noise in the sensor. Okay, and using this, we can calculate K. K is simply calculated as sigma K plus 1 HT into S minus 1. So this is the Kalman filter algorithm, right? So I know it looks complicated and I think I might have lost a few of you, right? Because I was just explaining the algorithm without an example. Okay, so what you need to remember is it has two steps. It has the prediction step and then it has the update step. What the prediction step does is it uses the motion model, the simple motion forward, while the update step uses the observation coming in. Right? So now that's all you really need to understand for now, because I'm going to do a simple 1D example and all of this will be a bit more clearer and easier to understand. Okay. All right, so let's do a simple 1D example. So let's say we had a robot on a 1D existence, right? So it's not 2D. Its pose is along this line. Okay, and I'm actually going to do the steps of the Kalman filter along with this, and it will be much more clearer for you guys, right? And I will give a handout by the end of this also that I think will be really helpful for you guys. Okay, so bear with me. Just remember there is the prediction step, and then there is an observation. Okay, so let's say the robot started at this point. Okay, and I'm going to call that xk. Right, and this is where the robot started. And I'm going to call it. Okay, so the robot can only move in one dimensions, right? So our pose is going to be a simple one-dimensional pose. It's not going to be a vector full of x, y, z, theta, none of that. It's just going to be this distance. So let's say its current location is xk, and a few minutes forward, it's going to be at xk plus 1. And there's going to be a delta t time taken between these two steps, right? And then at this location, it has some sort of observation, right? So let's say this robot has a sensor that can detect trees. Okay, so imagine this robot is here, right? It's at xk plus 1, right? And then let's say there's a tree here somewhere around. Let's say exactly here there's a tree. Let's say there's a tree. Okay, so let's say the robot can detect trees. Okay, so when the robot has a tree in front of it, it detects the tree. Right? So now let's say the robot is. So this is the. Let's say this is the. Let's say, yeah, let's say this is the actual location of the robot. Yeah, let's say this is, yeah, after delta t time, let's say this is the actual location of the robot. Okay, so what we are initially going to do is we are going to look at the Kalman filter algorithm, right? Now, in the recursive system, we need to, the answer that you get at the end gets put back into the system, right? So your xk plus 1 is what goes in the next step, right? So at the start, you need to have some sort of initial value that you have to start with, okay? So let's say we know this xk value that we're starting off with, or we got it from the previous step, okay? So let's go through the Kalman filter algorithm now, right? Okay. So imagine this robot is first moving forward, right, to this xk plus 1 location, and we had some sort of control signal u. Okay, so I'm going to make this very simple. I'm going to make the motion model the simplest possible motion model that you can consider. Okay, I'm just going to assume that xk plus 1 is simply going to be equal to xk plus uk. Right? So, for example, now let's say we make a prediction, right? So what are the quantities that we have? We have xk and we have uk. From this, what's the first step in the Kalman filter? Is the prediction step. So in the prediction step, what do? We take the motion model, right? And we make a prediction of where the next step is going to be, right? So we are going to say xk plus 1 bar is going to be equal to simply xk plus. Now I'm going to make a very simple motion model and say xk plus 1 is simply just going to be xk plus v, right? Imagine the encoder is telling me that I'll just put values here to make it easy, right? Imagine I was at 2 meters, and then the encoder says that I have moved 5 meters. So my xk plus 1 is going to be 7 meters, right? So very simply, your prediction is going to be I was at 2 meters, my encoder said 5 meters, and my answer is 7 meters. Right? So this is going to be my simple prediction. Right? My next step is going to be xk plus uk. right? And this is a simple motion model. In most cases, the motion models are more complicated. It could be a situation where it's like A into B plus UK or something like that, right? Somehow it's a function, right? All it does is it maps my previous location, my motion command to the current location. Okay, so I'm going to make it very simple and just say xk plus 1 is going to be equal to xk plus UK. Okay, and I'm just going to put a hat on the top of this because it's going to be some sort of estimate. We don't know the truth of it exactly, right? So remember, these values are just going to be the mean of the Gaussian, right? So when I said it was 2, this was 2, and this was 5, and this was 7, what I meant was there'll be a Gaussian like this. Gaussian's mean is 7. The Gaussian's mean here is 2. And this will also have a Gaussian, right? The control signal will have a Gaussian whose variance is determined by that value Q that I mentioned before, right? So the control noise. This is that noise, right? How much the control signal is varying. Okay. All right, so this is our prediction step. So we predicted that the robot has moved forward in time, right? Based on this control signal. Now, will this prediction be accurate? No, right? So imagine imagine this is the actual location of the robot, right? This is the actual location of the robot. But our prediction is always not going to be the actual location. It's going to be wrong, right? Because there is noise in the system and things like that. So let's say our prediction, this x bar k plus 1 is actually here, right? So this is the actual xk plus. What I've drawn in red is where it should be, but our prediction, because the noise in the encoder and all that stuff, assumes that we're here. So this is xk, this is xk plus. Cool. So we are actually, there's a small error here, you can see, right? And again, there's a, I'll actually draw the Gaussian here as well, right? So there'll be some sort of Gaussian here like this. And the mean of the Gaussian is what? Xk plus 1 is. Okay. Let me draw the Gaussian. All right. So this is the mean of that Gaussian. What about the variance of that Gaussian? That's the next thing that you predict, right? The next thing you predict is the variance of this Gaussian. All right. So how do you predict the variance of this Gaussian? Now assume that in the previous state, what are the inputs that you are giving into this as the Kalman filter algorithm? We are giving it xk, we are giving it sigma k, we are giving it uk, and then we are giving it observation z k plus 1. Okay, these are the inputs into the system, right? So we already use xk and uk, right? And at the same time, we can say that this control signal is what has the noise, right? So we put all the control signals noise. So I'll actually write the control signals noise. So just to explain, xk will be a normal distribution, right? Whose mean value will be xk and whose variance will be sigma k. And UK is also going to be a probability distribution, which has we call it a wide Gaussian noise. It will have a mean of 0 and it will have a variance, right? So that variance I'm going to call, let's call that simply, let me just double check the notation. Yeah, I'll call that sigma u. Okay, so what I'm trying to explain here is all these quantities are Gaussian distributions, right? So when we start off, when I say xk is in this location, it already has some sort of distribution, right? And now we are making this prediction and we want to, now we found the mean of it, we want to find its variance, right? So to find its variance, now remember what I did in the recap. What happens when you add these two random variables together? When you add these two random variables together, their means get added, right? So that's what I've done here. I've added the means, right? What about their noises, right? Their variances. What happens to the variances? The variances also get added, right? So this will simply be sigma k plus sigma mu square. Okay. Remember, if you take two Gaussians and you add them together, right, their variances get added as well, while their means get added. Okay. So if I take this prediction step, what is happening? If you started with xk, what's going to happen to its noise? Can someone tell me? Is it getting worse or getting better? When we move forward in this motion, right, and make this prediction using this motion model, is the answer getting worse or better? Is my estimate of my location getting worse or better? How many of you say it's getting better? Can you give me a thumbs up? Okay, how many of you say it's getting worse? Okay, we have 1, 2, 3. Yes, correct, right? Because you're adding two noises together, right? So remember, every time the robot moves forward, things get worse, right? So the prediction step always makes things worse, right? Because motion is inherently very noisy. There can be slip, there can be mistakes in measurement, all that stuff, right? So whenever a prediction happens, whenever the motion forward happens, there is going to always be an increase in the variance, right? So we can see that the variance increases. Whereas here, in the compared to the previous step, this is much more pushed aside. Okay, so this is the simple prediction step, right? So I hope this is clearer now when we are doing these steps. Okay, all right. Now we have the prediction. Now we'll go into the next step, which is what? What's the next step called? It's called update. Right. So in the update, first you need to calculate the Kalman gain and all that stuff, right? So I'll actually hopefully give you guys just the intuition behind this first before we actually do that, right? So when you do the update, what that means is now the tree is here, right? Okay. Now the sensor has noise as well, right? So where is the actual robot? The actual robot is here. Now let's say because of the sensor's noise, the actual robot sees a tree here, right? Because the sensor is not accurate. So it will shout, okay, I'm near the tree, right? So it will say it's near the tree, and there'll be a simple, again, an observation model that takes where you are and tells you what sort of observations that you're supposed to see, right? So in the update step, we have to look at, this was the motion model. We have to look at the observation model, right? So in the observation model, what we're saying is, where is my observation given where I am at the moment, right? So what the observation model will say is simply, I'll just move here and write the observation model, right? So your observation model is zk plus 1 equals xk plus 1 plus, again, some sort of noise, right? So in the previous case, we put sigma u k plus 1. So I'm going to say that the noise is, I call the noise Vk, right? And this Vk is simply a normally distributed thing, again with zero mean, but a variance of sigma z square, right? So that's the relationship here. What this is doing, it's taking your location and mapping it to the observation, right? But we need the kind of the opposite of it, right? Given my observation, where am I supposed to be is the question, right? Okay. So if this is the normal distribution, what I'm going to do is, given this observation, where am I supposed to be? I'm just going to simply take this to the other side, right? Zk plus 1 minus Vk, this noise, right? But when you put this minus here, what happens to this? Remember, if I had a distribution like this, if I just multiply it by a, all I get is a to the power mu, a into mu, a squared sigma squared, right? So just by taking this minus, this doesn't change. It will still be normally distributed with sigma z squared, right? Because you are multiplying this by -1 and multiplying this by -1 squared, right? So it will still stay the same. So what does this say? According to my observation, xk plus 1's location, right, will be normally distributed like this, right? What's the mean here? The mean is just going to be zk plus 1, right? And the variance is going to be sigma z squared. This is because I'm taking a very simple observation model. I'm saying wherever I observe the robot observes a tree is where I assume the location of the robot is going to be, right? Whatever observation. So simple example, let's say the tree is at 3 meters, right? So what this equation says is, if my observation says there is a tree at 3 meters, then I must be at 3 meters, right? This is again a very simple motion model. In reality, these motion models are more complicated because, for example, you will be seeing the tree from far away, right? Right. So this mapping of the observation to my location won't be one-to-one like this, right? But I'm just doing a very simple example. I'm saying wherever I observe a tree is where I am, right? So xk plus 1 plus a noise, right? So if this says 3 meters, then I am at 3 meters, right? Which is what I'm representing here, okay, by this normal distribution. So your location will actually be the observation with that noise. Right? So in your update step, what that means is, if you're getting an observation, let's say the observation you got is the tree, the observation will tell you that you're here. Right? So your control command says that you're here, your observation says that you're in front of the tree, right here. Where is your actual location? Your actual location is here. Right, so the observation is in light blue, the control command is in yellow, your actual location is red. And what we need, what the Kalman filter is going to do is we are going to combine these two, and the final result is going to be closer to the truth. It's going to be somewhere around here. Right? So what the update step is going to do now is it's going to combine the observation with the prediction. Right? So to understand this, we go back to this concept of information, right? So if I take the total information here, now there are two pieces of locations coming, right? One is coming from the control command, one is coming from the observation, right? So the control command is saying, this is where I am. The observation is saying, this is where I am. Okay. So what's the information from the observation? If I take the information from the observation, it's simply going to be 1 over sigma z squared. Again, I'll put a bar on top of these just because they are kind of predicted observations, right? So it will be sigma z squared, right? Actually, we don't need a bar there, right? Because this is the observations. So it will be sigma z squared, right? What about your control command? If I take the information coming from the prediction, right? It's simply going to be 1 over sigma k plus 1 square, right? So you can see that there are two Gaussians now, one from the control command, one from the observation, right? And these are the information that they both have, right? So the prediction has this amount of information, the observation has this amount of information. And what the update step will do is combine these two together, right? So how would you combine this information together, right? First, let's calculate the total information. If I have the total information here, it's simply 1 over sigma z squared plus 1 over sigma squared k plus 1. That's the total information in this system, right? Now, if I'm going to combine these two, right, what's the smartest way to do this? The smartest way to do this is, right, you use this information to weight which one you would consider better, right? So, for example, I hope you understand the concept of a weighting, right? So you weight something more important than the other based on whoever is more accurate, right? So by looking at this information, we can decide who is more accurate, right? Because if sigma z is very large, that means the observation is less accurate, has less information, right? So then we should trust our prediction more, right? But if our observation is more accurate, then we should trust our observation more, right? So what we're going to do simply to get our update step is to weight these two together, right? So our final answer, which is going to be x bar k plus x hat k plus 1, right, is simply going to be, right, I prediction, right, information that is predicted divided by I total into x bar k plus 1, right? So I'm weighting how much the prediction matters, right, plus I observation over I total into what I'm getting from the observation. In this case, z k plus 1, right? So because again, I'm taking a simple model where zk plus 1 equals xk plus 1. If it wasn't equal, then you have to put the function there, right? Some sort of function of zk plus 1 that maps the observation to the location, right? In this case, your observation and the location are the same, just to simplify this, right? When I say there is a tree here, that means I am in front of the tree. Okay, but I hope this makes it clear, right? What we are doing here is we are taking out of that total information, what is the weight that I'm going to give for the prediction and what is the weight I'm going to give for the observation. So whichever one is more powerful will factor into the final one, right? So it's kind of like finding an average, right? A weighted average between the two, between the prediction and the observation, right? And if you follow this, and you actually do the calculations, you end up with this Kalman filter algorithm, right? So what I would suggest, since we're running out of time, is I provide a handout for most of you all, is to follow through this 1D example, right? Like you can actually take the substitutions here, and you will see that you're getting the same Kalman filter equations, right? All right, so what I want you all to remember with the Kalman filter is there are two steps here. One is the prediction, which is with the motion model. It's predicting how much uncertainty the motion is going to provide. And then it takes an observation and looks at how much uncertainty is there in the observation, and then finds a weighted combination of the two. And then hopefully the combination of the two will be a better answer than if you would take one at a time, right? So in most cases, that's the case, right? So for example, in this case, you can see if you actually look at the typical example, what you see here in green is the prediction. What you see in the dotted line in blue is the observation, and your final result, it will be somewhere the combination of those two, right? And that's how the Kalman filter works. So as I mentioned, I'm just trying to give you guys a intuitive understanding of this, and I will give you this handout to actually read through the maths a little bit more deeply to understand, right? Because there is no time to go into everything, right? So having said that, let's quickly talk about the EKF before we finish, right? Because we are really running out of time. Okay. So the EKF, what it does is, now in this case, we had to assume two things. We assume that everything is Gaussian, right? Because for us to do these combinations that I showed you here, right, we all used all those properties of Gaussians, but in reality, these might not be Gaussians, right? The other assumption that we made is everything is linear. All these systems, right, like the motion model as well as the observation model are all linear. But out of these assumptions, number one, Gaussian, number two, linearity. This Gaussian assumption is a reasonable assumption to make, right? Because most sensors behave in this way. But the linearity assumption is a very bad assumption to make, right? Because in reality, in this 1D example, everything is linear. But think about a 2D, simple 2D example, right? Let's say the robot is here and the robot is moving here like this, right? And let's say the robot has an angle of theta here. Let's take theta k, and this is theta k plus 1. And this is x, and this is y. And we have a certain velocity that it moved, right? In a 2D example, if I take xk plus 1 and yk plus 1, you instantly see that there is a non-linearity here, right? Because xk plus 1 is going to be equal to xk plus delta time into velocity into cos theta k, while as yk plus 1 is going to be equal to yk plus delta t v sine theta k plus 1, right? So you can see this assumption of non-linearity is lost because there is a cos and a sine, right? So in most cases, this non-linearity is a problem, right? Because the reason non-linearity is a problem is because if you look at what does those motion models and observation models do, they map your xk into xk plus 1 or your xk into the observations, right? So if it was a nice linear graph like this, right, your initial thing will nicely get mapped from a Gaussian to a Gaussian, right? But if it's a non-linear graph like this, your Gaussian will become non-linear, right? So the EKF, the extended Kalman filter, solves this problem. So what the extended Kalman filter does is it at this point where the mean is, it approximates a linear graph, right? So instead of the actual motion model is non-linear, but it makes a approximation of this curve around this point, right? So if you look here, I think there's a diagram here, right? So it makes a, so for example, you can take any curve and you can approximate it as a linear function, right? So what it does is it's the same as the Kalman filter, right? But there's this added step where it takes those functions and makes those functions linear. It approximates it to linear. And that way you can still make the Kalman filter work, but under another new assumption or a new approximation that turns everything into linear curves, right? But you can see here that that's again not a very good thing to do. It's an approximation, right? The further these values are away from the normal, that approximation falls apart, right? So for example, if this curve had a very large uncertainty, your approximation will be bad, right? It will fall apart. Okay, so that's about the EKF, and I'll give you guys a handout for that as well. Okay. All right. So I hope that gives you an idea of the EKF and the Kalman filter, right? So I'll quickly summarize everything now and show you guys a couple of videos and some practical things to think about when you are designing these filters. All right. So just to give you a quick summary of what we're talking about. Right? I hope you understand the importance of probability in robotics, right? Because everything is uncertain. We need to be able to deal with this uncertainty, right? Our sensor information is uncertain. Our control information is uncertain, right? So we need to be able to understand probability in robotics, right? So this is a field called probabilistic robotics, right? And then we learned some important things in probability theory. Right, we learned about Gaussians, right, and normal distributions, and how what matters in a Gaussian is its mean and its mean and its variance. This is if it's in a 1D situation. In a not a 1D situation, in a multivariate Gaussian, this mean will be a vector, and we have something called a covariance matrix. Right? It's actually without this covariance. Okay. And then we learned a simple example of the Kalman filter. And I want you all to remember it has two steps. It does a prediction. And then it does what we call an update step. In the prediction, it uses the motion, the control signal, to predict where it's going to move forward, right? Including the noise that is there in the control signal. In the update, it takes the observations, right, from the sensor information. And then it updates this control-based prediction to get a better answer. And all of this is done recursively, right? So you start in a previous step, you predict the next step. So you make a prediction, you update it, and that gets put into this system again, and it flows, right? And typically the prediction increases our uncertainty while the observation coming in reduces our uncertainty, right? And then we learned very quickly about the extended Kalman filter, which takes away this assumption of linearity, right? So how it does that is it approximates all the motion models and the observation models as linear, right? So a few things to think about practically. I'll just show you guys a quick video of a Kalman filter based system that I was using in my PhD. I'll quickly show you guys a video to show you practically how this happens, right? So in this video, you will see this is actually a Kalman filter based system. And some of the practical things you have to think about is you have to pick your sensors very carefully. You need to make sure your sensors give in more information and are very accurate, right? Because the control signals or the control information coming from the encoders and the IMUs are going to be very noisy. So you always have to pick some very good sensors to deal with, right? So let me just show you guys. Can everyone see the video?
Yes, sir, we can.
So I will end with this. Sorry, I took a little longer. There's a lot of things to cover. So in this case, this is me driving my robot, and you can see here what it's doing is just like the tree example I told you. It has some cameras here that look at these trees and these lampposts, and it's able to recognize them, right? So what we see here in green is the localization estimate, and you can see by purely using the control signals as well as the trees, it's managing to carry out localization, while as this yellow line is GPS, right? So GPS, as you can see, is very inaccurate, right? So the GPS signals, especially in the city, is very, very inaccurate, right? Because there are buildings everywhere, the GPS signal, if any of you use Google Maps outside, you know that it's not very accurate. Right. So by looking at these trees and these lampposts, you can get a more accurate response location estimate. But here you can see, since there are no trees, there are no observations, all it can do is rely on the control commands, right? The motion commands. And as a result, you can see it starts to drift away. So that's like covering your eyes and counting your steps, right? Because there are no red dots here. The red dots are the trees and the lampposts, right? So the moment there are less observations, you can see that the answer is getting worse, right? So this is another quick way of looking at it. So what you see in green is the mean, right? So what you saw here is the mean location. But in this next, it's the same video again, but I've removed the map. And here what we're going to see is the mean location as well as the sigma value, the uncertainty. Right, so hold on. Right? You can see here when the observations reduce, can you see the purple color lines? The purple color thing shows the uncertainty, right? So although the green is saying this is where I am, the purple is saying it can be in this general area, right? So now you can see here when it comes to this area, there are not many observations. This purple area starts to become bigger and bigger, right? So instead of me saying, I know exactly where I am, what this purple area is saying is the mean is here in the green area, but it can be anywhere in this purple area, right? This is the Gaussian distribution, basically, right? So the green is the mean. So the Kalman filter is estimating both of those things. It's estimating the mean as well as the uncertainty, right? So in these areas, the uncertainty is very, very small. Why? Because there are many observations. But now as the observations drop, you can see this is increasing. But now when it comes here, it starts to see these trees again, right? And you will notice everything becomes smaller. Right? So hold on. Right? And now you can see that it corrected itself and the observations become better, has improved the answer, right? So that's a simple example of the Kalman filter in action. So I hope this was useful. It was a lot of material to cover in 2 hours. Thank you for listening, and for further reading, I will provide, I think, the organizers with some references and maybe some links to some videos and some handouts. So if any of you are interested, you can read them to get more information. more in-depth information, because there's a lot of theory here that is very hard to tell in like 2 hours. But I hope I have given you a very intuitive, basic understanding of why probability is important in robotics and why estimators are important, because instead of finding the exact values, we are finding the uncertainty and the probability around these estimations. So with that, thank you very much for listening. Sorry, I took a little longer than usual. So thanks a lot, everyone, for listening.
Thank you very much, sir, for that very informative and interesting session. They have also sent us a few questions through the link we have provided. And if there's anyone who has missed sending us questions, you can scan the QR code and send them to us. And the first question is, how do we handle the matrix operations if one of our sensors fail to give us a reading? That is, if one of our state variables are missing.
Yeah, so usually the update step is done when you get an observation, right? So it's usually handled, usually handled step by step. If the sensor information is not coming, we would just continue to do the prediction. So in the video that you saw, that's what happens when no observations are coming. And you saw what happens, basically, it only starts to rely on the prediction only. And because it starts to rely on the prediction only, it becomes more and more and more uncertain, and it starts to grow and it starts to drift, right? Again, think about it as covering your eyes and counting your steps, right? The moment observation comes is when you open your eyes and sense information is coming into the system, right? So if the sensors fail to give us a reading, we don't do the update, right? We don't take in the sensor information. And we rely on probability only. I mean, sometimes it can go wrong, right? So it's actually better than not thinking about probability, right? Because if we pretend like everything is 100% accurate, then we are in actual trouble. But accepting the fact that we'll never know the answer properly, but we will have a guess of it, and having an idea of the answer actually is a very, very powerful tool, because it makes us remember. I said there's a system in the robot called a decision making and motion planning system, right? So if you tell that decision making motion planning system how uncertain or certain they are, it can make a more intelligent decision, right? So actually taking probability is an important aspect, and it's better than not taking. Okay, what kind of programming language do you suggest to learn if you're interested in one? Okay, so C++ is probably the best language to learn for when you're actually trying to build a robot. The main reason is one of the biggest software tools now in robotics, both in the industry as well as in academics, is called ROS. ROS, I hope some of you have heard of ROS. ROS stands for Robot Operating System. You can just Google it now or check on YouTube. It was invented in 2012, right? And ROS is a very powerful tool that helps build robots very fast. And one of the main programming languages we use in ROS is C++. But ROS can also be used with Python and MATLAB and things like that as well. But if you are really working with the hardware, C++ is important. But having said that, Python is also a good language, because ROS works with Python as well. So ROS and OpenCV and all these libraries have both Python and C++. So what my suggestion would be Python is very easy. So to start with Python, and Python will help you to build robots really, really, really fast, because you don't have to worry about the language that much. Python is very simple language, but C++ is more complicated, so it will take a bit more time. But if you're making, say, a robot in the industry level, C++ is important, because C++ is faster and more efficient. But if you all are learning and being in academics and trying to learn a language, I think Python is good. So my suggestion would be learn Python and ROS and OpenCV and things like that with Python, and then take a step up and learn C++ once you're more confident. what are the technical skills we have to develop other than a good GPA to pursue a PhD in robotics? I would say GPA, and if you can have 1 or 2 publications. Okay. So if you all are interested in academics, I think the best thing to do is try and get at least 1 publication with your final year project. But having said that, usually in the PhD, the first year or so is there for you to learn. So in most cases, you don't have to know everything going into the PhD. And you won't know everything ever. Like I don't know everything yet either in robotics, right? I just did my PhD. And for the most part, you will always be learning. So try to learn as much as you can before going to the PhD. But usually that first year, you have a chance to learn by yourself a lot of things as well, right? But get a good GPA, try to get a few publications if possible. That will help your application. And if you really want to get into robotics, the resources that I will send you guys, I will send it to the organizers, and think maybe we have your email addresses and we can distribute it. There's one textbook in particular. It's called Probabilistic Robotics. It's a very good textbook. If you read through it, I think it will be a very good resource when you're applying for your PhD. Okay, but theoretical concepts, theories would be suggested to dig deeper into and research into understand and appendix the knowledge what was discussed today. Yeah, so I think these theoretical concepts of probability and statistics is really important. And I think anyone who wants to build actual machines in the real world has to get better at probability and statistics. And unfortunately, it's some area that most of us are not good at. It took me a little while to get good at it as well, right? So I would say that theoretical concept, I think probability statistics and how to think about stochastic systems is really important. Next question. Using probability means using AI algorithms, right? Or are they different from estimator algorithms? So AI algorithms are actually different from estimator algorithms. It's actually the complete opposite, right? So in estimators, you are dealing with probability, you are unsure, and you're trying your best to estimate things that are unsure. In AI, most AI algorithms, what you do is you feed in a bunch of examples. Like, this is called supervised learning, and you get the algorithm to learn the patterns. So the algorithm doesn't predict any probability information at all, right? It just looks at examples and can make predictions based on those examples, right? So it's kind of like if I show a lot of pictures to a computer algorithm of apples, then that algorithm gets better and better at picking out an apple in a photograph, right? So it doesn't do this in probabilistic way. It can't, it purely depends on how many apple pictures to show it, right? And the model of the AI, most AI deep learning algorithms don't have any probability information coming out of it at all, which is kind of a problem at the moment that most people are researching into and trying to get better at. Because as I mentioned, if it's just giving an answer and we don't know how sure it is of that answer, that's a very bad design, right? So most of the AI systems are really good at doing specific tasks like object recognition, things like that. But it's not good at tasks like localization, the kind of thing that I showed you, right? Because these AI systems are kind of like a black box. You feed it information and it gives an answer. But how sure you are of that answer or anything is not very clear at the moment. But it's a very big research area right now to try and include probability into most of these AI algorithms. And there are some examples of this already happening. But it's kind of two different approaches. I hope that answers the question. Also, should I share the resources with you guys on Zoom or what's better?
Can one of our committee members answer to that?
Yes, sir. If you can send the PDFs, we can share it among the participants.
Okay, good. So I will send you guys an email with a couple of PDFs, one textbook that is really useful. So when I share, I'm showing you guys pictures from that textbook. So especially if anyone is interested in a PhD in robotics, that textbook is the textbook to kind of follow because it's kind of like the Bible of robotics. So if you read that, you'll get a good information. And then I'll also give some small handouts on the Kalman filter specifically. So if you are just interested in that, but you can read that. And then I will give a series of videos on YouTube that I think I will use. So I'll send all of that in an email to one of the organizers and we can share it with them.
Thank you, sir. And with that, the Q&A session is concluded. I have a small request to be made. Please fill the feedback form and give us your valuable feedback. You can now access it through the link displayed in the chat box. Also, we will share the resources with you. And with that, we have almost arrived at the end of today's session. It's time to conclude our webinar, which was an immense success indeed. On behalf of our society, I would like to thank Dr. Maleen Jayasuriya for joining us today. Despite your busy schedules, we learned a lot about probabilistic robotics, probability theory, Kalman filter, extended Kalman filter, and practical considerations in filter design. I'm sure that estimated design will not sound novel to any of our participants anymore. Dear sir, please accept our token of appreciation presented to you by the Robotics and Automation Society of University of Peradeniya.
Thank you, and thanks a lot. This was a lot of fun. I wish I had more time, and sorry if it was a bit rushed, but thank you.
Moreover, a huge thank you goes to all of our participants who attended this evening. Without you, this event would not have been a success. Last but not least, I would like to thank all the members of the Robotics and Automation Society who work hard towards the success of this webinar, overseeing all the events. Again, I would like to remind you to participate in our Webbots evaluation task to win valuable prizes. The registration deadline has been extended until 4th of September. For further details, visit our website. You can now access it through the QR code. Before winding up the session, I would like to remind you that the third and the final day of Phase 2 of Robotricks 2021 webinar series is scheduled to be held soon. There, we hope to give you the knowledge about linear control techniques and implementation. Join us in the upcoming webinars as well to gain extensive knowledge in the field of robotics. Now it is time to conclude this webinar. Hope to meet you all the next day with the same enthusiasm. Stay safe, everyone, and have a good night.